Today we are going to see the experiment on performance assessment of grid connected and standalone 1 kilowatt peak power systems. This is for Renewable Energy Systems Laboratory syllabus raised by Anna University, Chennai. Right? The scale of the simulation is UG students beginners level. The scale of simulation is UG students beginners level. Now we are going to see the experiment, right? So before starting to that simulation, experiment on performance assessment of grid connector and standalone. First, we are going to see the standalone 1 kilowatt peak power system, right? So this is the PV system. We have subdivided into major two categories. One is grid connected, another one is standalone system. This standalone system further subdivided into with battery based system, next without battery based system. With battery based standalone schemes is further classified into DC system self-regulating, AC system with charge controller for battery and load. Without battery, the direct coupled system, right? So the next one is hybrid PV system. We will see on later. Now we are going to see the standalone system with the battery and AC system with the charge controller for battery and load. So we need the basic functional block diagram of this experiment. This is the PV panel. It may be get the irradiation from the solar sun. So the PV current will fed into the battery charger. This is nothing but a one nodal point. From this nodal point, the inverter is connected. The output of the inverter is connected to the AC load. Again, the battery which may be going to integrated through this nodal point through the battery charge controller. Now we are going to draw this circuit in MATLAB simulation file, right? So this is as per that is earlier we are seen. Now we are going to see that is the Simulink browser. In my earlier video, how the Simulink browser will be open and untitled page, everything we are already seen, right? So first of all, that is untitled page will be erased. Okay. Now we are going to draw this diagram. Draw this diagram in Simulink. So the first we need the solar panel. Where we are going to get the solar panel? This is the Simulink library browser. In the SimCap tab. In the SimCap tab, that is, this is the SimCap. In the SimCap, again further that is subdivided into electrical. Again, that electrical technology is subdivided into specialized power system. In this category, we have that is the renewables. Here, that is the solar PV panel which is available. Now, I am drag and place this PV panel, right? So here, that is the in our experiment, that is there says the 1 kilowatt peak power. Now we are going to fix this 1 kilowatt peak power in this module. How we are going to set this value? So first of all, I am also, what is the, in earlier case, I am going to fix the 10 watts panel into number of strings and number of rows. So different things we are going to see, right? So that is the model is already existing model. Now I am going to select the user defined model. So the open circuit voltage, that is 21.5, and the maximum voltage, the maximum power point voltage, which means during the time of maximum power notch point, the voltage supplied by the PV is 17.7 volt. Similarly, that is, we are going to take as 0.65. Again, the current at maximum power point, so that is 0.57, 0.57, right? So this is that the values we need. So now we are going to, so the one panel having this value, one panel having this value. So now you may going to click the apply. So here, what is the power, maximum power? 10 into 10.089. But we are going to develop the module, that is how many panels will be connected in series, how many panels is connected in parallel, we will decide. So based on our requirement, again we are going to that the circuit. So in our system, the inverter output all our electrical apparatus in our country, in our voltage system is 230 volt RMS system. What is the value? That is the 230 volt RMS system. So that is the main point we are going to consider, 230 volt. So 230 volt RMS. So this RMS into, we are convert into the peak value. So peak value. So how we are going to convert 230 into SQRT, square root of 2, which means peak value, that is 230 into square root of 2. What is the value? So that is the value for the peak voltage. So I want to get this the value from here, that is this is CLC. So I am also enter this 230, which means the RMS value of AC system into square root of 2. So what is the value? 325.2 volt we need. 325 volt we need. Now we are going to see that is our panel. So double click. So what is the value of this? That is the, during the maximum power point tracking, that is 17.7 volt. But actually we need the maximum peak voltage is 325.2691. So I am going to compute the how many number of modules will be connected in series. So divided by 17.7. So what is the value? 18.376 modules. So we are going to round up the value of 19 modules. So 19 modules. So now I am also going to connect it in the that is 19 modules connected in the series. Now that is, what is that the each module having a range, having the range of, what is the range? So that is 190. That is each module having a 10 watts. So now we are going to compute 19 into 10. As usual, you are well known, 190 watts. But how many parallel strings we need? So that is 1 kilowatt peak power system. One, two. So 1000 divided by, so 1000 divided by, so each series string having a, that is 190 watts. So how many rigs which are needed for get the 1 kilowatt power, that is 190. So that is enter, that is 5.26 32 rigs, that is parallel modules we need. So we are going to round off the value of 6, round off the value of 6. So I am going to fix the 6 parallel strings we needed, 6 parallel 6 we needed. So that is I am going to apply now, apply this value, test what we are going to test, what is the PV curve value, right? So here we are obtain the PV curve. Here we are going to obtain what is the voltage, that is 336.3 at the range of 1150 watts. Our aim is 1 kilowatt, but here 1.15 kilowatt we are designed, there is no problem, right? So that is here 336.3, and we are getting the amps. What is the amps? For 3.42 amps, right? So, okay, right. Now we are going to do that, draw the other system. So what is this? Each module having a forward blocking diode. So forward blocking diode. So for that purpose, I am also going to drag that the power electronics. This is the power electronics. This is the diode, power diode. I am drag the diode from that the system. So here, so I am double click this diode, remove the show measurement, and that is 1 e to the power of 5 for snowball resistance. So I am changing the snowball resistance value. Again, it may be going to connector, right? So what is the our aim? That is, we are going to develop this circuit, right? The charge controller, inverter, and then that. First we are connected to the inverter. Again, the charge controller will be connected in parallel with the system. Okay. So first, that is next we need that the inverter circuit. So that inverter circuit we are obtained from that power electronics blocks. So this is the power electronic block. So here this is universal bridge. Why it's the name is called is a universal bridge? This bridge contains the rectifying option, the inverter operation. So, and also the diodes, everything it is available, the IGBT, MOSFET, and everything. So for that purpose, this block is called as the universal bridge. This is this, we are going to develop the single phase system. So here I am also going to change MOSFETs and diode. So this is the snowball circuit and everything. Now I am going to apply, right? Apply, then okay. So I am going to rotate this module by pressing the Control R key. Control R key, right? This is the, but here keep it in your mind. This is plus and this one is minus. You have going to, but here this is the plus and this one is minus. You may going to connect in very carefully. So that is very important. Now I am going to connect this system in the positive to positive. Again, that is, again I am also going to connect this system from negative to, that is negative, right? So this is the option we are used for that the purpose. We are used for that our purpose, positive and negative. Now the next thing, we are going to connect this output through the LC filter. So L and C. So where we are going to form, that is this is the element, the RLC series branch. Drag this element and placed in this place, and double click, and I am double click. So I am going to select the L module at the range of, I am selecting the 5 millihenry. That is the, suppose I am going to select that 5 millihenry for that in our designs. So again I need that the element for the capacitor RLC series branch. This branch will be rotated by pressing the control R button. Control R button I have rotated. Again I am press this the right click and drag it. I'm going to get the another module, right? So next double click. So this is the thing, that is the C capacitor. So in the capacitor, that is the 2.5 microfarad, I am setting this value again. So this is the output. So what is the output? Here we are fixing the value of the R value. R. This is the R where resistance is 1, but it is not possible to give the 1 ohm. Then we are going to find what is that. The power is 1 kilowatt. So 1 kilowatt divided by RMS voltage is 230. Enter. That is 4.378 amps. Again 230 divided by this 4.3. This 4.3. Yes. Now I am going to divide by 4.378 amps, which is equal to 52 ohms, 52 to 53 ohms, right? So for that purpose, I am also going to fix the 52 ohms for here, right? So next, that is how we are going to develop this. So this now I am going to connect this output from L. Again this is that connection. So this is the another point of view, that is that B and A is to be connected here. Now I need the measurement. So the next one step is we need the that is the gate signal. So how we are going to develop that the gate signal? So sinusoidal pulse width modulation. This sinusoidal pulse width modulation, I am going to get the this sinusoidal pulse width modulation from the block of that is pulse and signal generation. That is the PWM generator for 3 level. I have dragged this module and then double click. So here which is available 27 into 60, but I have fixed some that the 1 kilohertz is a carrier frequency, 1 kilohertz, but the bridge is, that is the 4 pulse only we are needed. So apply, then okay. Now we are giving the input for sine wave. How we are going to generate the sine wave? Due to time limitation, due to that is here we are going to feed the sine wave for this getting that the sinusoidal pulse width modulation. So the sine wave equation is, the basic criteria for that sine wave equation is, that is sine of 2 star then pi star f, which means here that is the frequency f, start then t time. This is the sine wave model of that equation. So here, how can I set this sine wave? That is the subsystems modules which is available here. That is user defined function. This is the user defined function which is available in the MATLAB. I am also going to select this. So I am going drag and drop, and then connect the system. So here, that is I want to feed the what is this the same equations we are developing, the sine 2 pi f t. So here that is here which is available, sine 2 pi f t, but this is a capsule letter which is available. So again I am also going to fix sine 2, this is a small letters, otherwise the error will become sine 2 pi f which is nothing but the frequency, t is a time, but the time is which is derived from the external signal, so u of 1. Next I am also going to multiply the entire system by u of 2, that is magnitude u of 2. Here the sine wave equation which is called as the entire equation which is multiplied by the magnitude, that is what is its magnitude, that is 230 or some other things. So specifically it may be called in 230 based system. So for that purpose u of 2 here I am going to give on, right? Now we are going to see. So this is the way we are going to obtain this t value. So this is commonly block. This is the max which is available, because I'm drag and drop this max, drag and drop. Yes, here that is the two inputs we are going to given. First input is, what is the first input? U of 1 is the t, u of 2 is magnitude. So in source, that is the t time clock which is available. I am also going to feed this time clock here. The next thing is that what is the magnitude? That magnitude which may be going to adjusted, that is the constant. So this constant which may going to connect here, but the value is varied from 0 to 1. How the value is varied? That is SLIDER, slider. You can type and then search for the slider. So the slider option which is available, drag, and then you can get this slider. You can get this slider. We are going to connect this slider to this constant. See, you may click this box. Again, which element you want to connect, I am going to click this element, constant. Again, I am going to select this constant. The minimum value is 0, maximum value is 1. So apply this value, again OK, right? So this is the sine wave which is connected, the pulse is connected in this circuit. Again, that is this is the system. The next thing I am also going to connect this, the irradiation value. Irradiation is 1000 watts per meter square, right? Now I need the voltmeter and ammeter for measurement purpose. Measurement I am going to, before connecting the voltmeter and ammeter, I am going to connect the battery of the system. It is very, very important. So how we are going to connect the battery? So in the source, electrical source, this is the extra electrical source. That is the battery which is available here. I'm going to press the control R. So the terminal is reversed. The battery is charged by the charge controller. I am going to select this charge controller. So this charge controller, this is the very important point. I am going to set the values. How I can set the values? Please see. So this is custom specification. I'm going to set the DC unit. So here that is the 325, that is the voltage, and this is the ripple frequency and other thing. Charging current is based on this voltage. So I am also going to fix the voltage. What is that? The voltage, nominal voltage is a 320. The rated capacity I am also going to 2.5 Ah. So this is the apply the status of that system. I am going to respond for 1 second. Initially, that is the battery assumed as a 75% of charging. Again, double click this charging system. So I am going to fix that is the current. What is the current? 2.8. So for here I am also fix the, that is the 5 amps, right? So that is the output. The overshoot time and the settling time is 5. Settling time I am going to change 1 second. This is the input. Again I am going to apply. So this is the entire value, but this is greater than the 1500. But how we are going to fix this nominal power? That is 5 into 138, which means that is a very large value. That is 500, around 750. That is 750 apply. So this is suppose if you are going to give the 100, you may create some other problem during that time of operations. So for that purpose, at least that is the 750 is best, and 250 will also going to given the system. So this is that the thing. This is the custom specifications. This is the DC plot apply and the TA values. So what is this? The entire thing is changed. This is that the entire thing is changed, frequency and everything. Suppose primary mix, or if it is in the tristonic, again that is it can be changed. But here that is we are going to fix that the custom device. So custom device, and also we are taken as a input for the DC. So then apply. So here now we are going to get the positive and negative. So this positive signal which may going to connect here, that is this positive. Again this negative we are going to connect for here. So this is which is available. The entire system we need the voltage measurement and the current measurement. So already we are seeing how we are going to measure that the voltage and the current. Simply that is the measurement. That is normal measurement which is available here. That is current. If you need that the current, I am also going to measure the current here. That is that here, that is the ammeter. Again I am also going to connect this ammeter here. So remove. Similarly, that is the measurement system. If you want to measure the voltage, again we are going to measure the voltage. So this is that the voltage measurement which is connector, right? Now connector. Similarly, that is the again this point we are going to connect the voltage of the system. So now due to time limitation, because now itself the recording time is 29 minutes, it is difficult to that. I am also already I got it. So that is the entire circuit which may be drawn. Now we are going to run the a simulation from here. That is I am going to run, right? So now the simulation is compiling. Right now it may ready to start running. Now it can be running. During that time, that is, I am changed the 0.5 as a modulation index. Again, that is, it may change it as 1. So one small dip is I am also fixed. So here you may see that is the that is the current drawn by the device will be reduced during that time. At the same time, the output of that device voltage which may be affected, and also the current will also going to be affected. So this is the process of the PV based that is a standalone system. At the same time, the charge controller which can be maintained the 350 voltage, and that the DOC and other things we are maintained in the proper manner. This is the this entire system which may be called as that PV standalone system. That is, PV is connected, again the charge controller, this is the battery, again the inverter, this is that the LC filter, that is LC filter concept, then the output load is connected. So the entire setup which is going to see as per the Anna University syllabus, that is the experimental performance on that standalone PV system with the open loop configuration, UG level, UG students and the beginners level. Okay.